Hey guys, this is AP Bio. Welcome back to class. And today I believe this is going to be for Wednesday, September the 23rd. So I hope you guys are ready for some more math. We're taking a look at our calendar right now for September the 23rd. Popped it out here, made it a little bit bigger. And for September the 23rd, our goal is to look at chi-squared and comparative statistics. So hopefully you remember last week how we covered what we called descriptive statistics, how you could describe a set of numbers. And now we're trying to learn how to use statistics to compare sets of numbers, which is also really important in biology and any science. There is a virtual lab. It's chi-squared with M&Ms. And when I do this in class, I bring a bag of M&Ms for everybody. As it is right now, I have a bag of M&Ms for myself, and you're going to have to take my data, and you don't get to eat my M&Ms. So sorry about that. Our essential question we're trying to ask: was someone messing with my M&Ms? We're going to be able to use math to figure out if anybody has been stealing their blues or something like that. So that is our goal. There is a lab. This is another one that can be kind of tricky sometimes. Last time we did a math lab, for the descriptive statistics, I had people asking excellent questions in the synchronous time. So please, please, please come and see me in the synchronous time, and we can go over this kind of stuff. So here are the notes. It's not super long. It's basically an example of what this is and why it even exists. So I'm going to try to get it set up here for us and for annotating. Okay, so let's see. Yep, it's working. Undo and mouse. Okay, so this is called comparative statistics, and we call it chi-squared, which is the formula or the value that we're calculating. What chi means is actually a Greek number, which you will also see written as this. I have had people think that that means let's square chi-squared to get chi-squared. That doesn't have anything to do with it. I don't actually know where the name comes from. I mean, I guess it comes from part of the math that you're doing when you're doing this. But don't square it. The value is known as chi-squared, okay? And that you'll either see it as chi or as that x with the kind of squiggly line in one straight line. So, okay, so let's talk about gambling. Gambling is like a really easy, like non-biology way to kind of figure out what this thing is. So we're gonna have a super simple gambling question. I don't know that they have games like this in Vegas, and they probably do. But this is a game of flipping a coin. Okay, we're gonna flip a coin. If you guess correct, I give you $1. If you guess wrong, you give me $1. Let's see, guess wrong, I give, guess correct, I give you $1. Guess wrong, that doesn't make sense. Doesn't matter. If you get right, you get $1. If you get it wrong, you give me $1. And let's just imagine we did this game, and if we flip the coin 2 times, and maybe it comes up with 2 heads and 0 tails. Okay, well that could easily happen. Like, that's not a big deal. That I would expect that to happen, and I would predict that to happen actually 1/4 of the time that I did this, and that gets into the rule of multiplication that we'll cover later on. If we flipped it 20 times, and I got 20 heads and 0 tails, then you might start thinking this game isn't fair. And it'd be pretty easy to tell. Like, it's very unlikely, and we could do the math very easily. It would be 0.5 times 0.5 times 0.5, 20 times, and whatever that would be. But we can just look at the numbers and think, well, no, that's not a fair game. That coin is unfair. It's not always as easy to tell, though. For instance, if I flipped a coin 200 times and I got 125 heads, and if I got 75 tails, well, that certainly isn't what I expect when I would expect, and I'm using the word expect here because this is my observations and my expectations. Then it's different than what I expect, but is it different enough to say that it's like unfair, that we don't want to play this game because it's unfair? And that means that we are going to use math to compare observed versus expected values. And so you have to be able to figure out both of those. In this case, like, our experiment is the coin flip, where we get the data, and that is our observed values, and our expected values come from our understanding of how this process works. Later on, we'll see that observed or expected values come from genetics crosses and Punnett squares is a really common way of doing it. Some evolution questions can give you your expected values. But the question we're trying to answer is, are the deviations that we observe in comparing observed and expected values due to randomness in the universe, how the universe is just random, a coin is random, and one flip does not affect the second flip or the third flip or the fourth flip? Or is it due to some variable affecting the outcome? And it's very tricky to answer that question when, like, we have something like we have over here, where it's 125 and 75. Certainly different than 100 and 100, but is it different enough? So the math that we're going to do looks like, oh, first we got to talk about a hypothesis. Okay, so in this case, we're going to talk about a statistical hypothesis and a null hypothesis. Null meaning it's kind of like a modifier that means not, or the opposite of. So they're not the same thing as your experimental hypothesis. So if we go through this, and let's just focus on this bottom row right here. We're not going to do the top two. Those are just examples to kind of build up to the idea. If I flip a coin 200 times, then I will get 100 heads and 100 tails. Okay, that's an experimental hypothesis. That's an if-then statement, right? And that can be confirmed, or it can be rejected by doing the experiment. But then when you get to the statistics of proving that, sometimes it's easier to start with a null hypothesis, because this doesn't ever really change. It always stays the same. And in fact, College Board has said, no matter what, if we ask you for a null hypothesis, you can put this. And even for any experiment, it doesn't make any difference. You put this and you get points, you get credit. There is no statistical difference between observed and expected values. And you can stop right there. We could continue and say any difference is due to random chance. And that means that the difference here of 125 and 100 is due to random chance. That's our null hypothesis, that like nothing's happening and there's nothing affecting it, it's just randomness. So that means that our hypothesis is the opposite of that. So these two have to be opposites. And this is, again, the statistical hypothesis, not necessarily your experimental hypothesis. And I kind of wish they had different names, but they're so closely connected that it's fine. Basically, we're saying here that the coin is not fair, okay? Well, because the opposite of differences are due to random chance is that the differences are not due to random chance, and that would be that it is not fair. So it's pretty common for College Board to ask you these kind of things. They make it very, very clear if you're talking about the statistics right here, or if you're talking about this with like, what do you expect to happen, that kind of thing. So it's really very, very, like, they're good about making that kind of thing clear, and I will try to do the same thing. So, all right, so then if we move forward, we get to the formula right here. And sometimes we get confused by big formulas right here, but it doesn't have to be. This right here is the formula, is the value we're looking for, that is chi-squared, is equal to the sum, that's an M, sum of, that means you're adding up, the observed minus the expected divided by the expected values. And remember, up here we have all these numbers. It's really just using observed and expected. We have the observed and expected values. We have two sets of them, so we should be adding these up. And I'm going to write this entire thing out, trying to do this with a mouse and a pen and you know, drawing over this, but I think it's helpful to see what this would actually look like. Okay, so we have chi-squared is equal to, I'm going to put the plus right here. So that's the sum of, because we're going to do this twice. And let's do the first column first, the heads. Well, we observed 125 minus the expected was 100 squared over the expected, which is 100. Okay, because it's the sum of, we're going to do this twice, and we get, by the way, I have no idea what the values are going to be. I made these numbers up, and that's fine. 75 observed right there, minus expected right there, squared over 100. Okay, so that's the math that you do. Remember your order of operations, subtraction, because it's inside the parentheses, PEMDAS, and so you get 25 squared over 100 plus 25 squared over 100. Okay, I'm not going to flip off of this tab. I don't have my calculator's out of batteries, so let's see what that would be. That would be 625 divided by 100. So we get 6.25 plus 6.25 equals 12.5 equals chi-squared. So our chi-squared value is 12.5, okay? Yeah, we did it, right? We did it. We've got a chi-squared value by itself that gives you absolutely nothing. And so now we have a value. We have a value that represents the differences squared of the observed and expected values. Why that matters is that we can then take that and use a statistical table called a p-table that looks like this. And it gives you the probabilities of random chance occurrences based on chi-squared values and something called degrees of freedom. Okay, so let's see what this is. Basically, inside the box are your chi-squared values right here. Those are chi-squared values right there, okay? Degrees of freedom is a measure of the experiment. And basically, it is the number of options, the number of outcomes that an experiment can have minus one. And so you can either get a heads or tails. And so that's two possible outcomes, and so we subtract one, and so you have 1 degree of freedom in this experiment. That means the chi-squared value that we're looking for is going to be somewhere in this row, although it may not be, and we don't care about any of the rest of it. It may not be exactly there, so you're kind of looking for the closest to it, basically. So. And so if we look, remember our chi-squared value was 12.5, I think, or at least close to that. And so we go in this row and we go, well, it's much bigger than that, bigger than that, bigger than that, bigger than that. And so we're all the way past here. And so if we just want to go ahead and circle this one right here because it's the closest one to it, that's our chi-squared value. And that means our p-value, which is right up here, is the probability of these results happening due to random chance. Or this would happen because we're actually further over here, less than 1% of the time due to random chance only. Okay, that's what the p-value means. So if we did this experiment, like let's say 100 times, right? If we flipped a coin 200 times as an experiment and we did that 100 times, we would expect results this far away from the expected, less than 1 out of those 100 times, and probably much less. It'd be more like less than 1 out of 1,000 times that we did this would we get 100 heads or 125 heads and 75 tails. And I drew a line right here because there's usually a line drawn on the p-table, because if you are to the right of this line, scientists a long time ago decided that 5% was a really good value. The scientists that decided this had better reasons for that I don't understand, but they said as long as we can say that these results would only happen randomly 5% of the time, then we can be 95% sure and go ahead and accept our hypothesis and reject the null. So that means we're rejecting the null, which means that, that we're rejecting the statement that these results are due to random chance. They are not due to random chance. And this coin is unfair. Do not play this game, okay? That's how this works. And that was a lot of stuff, and practice is what we need. So let's talk about the M&Ms, okay? I believe that is the last thing I had here. So, all right. If I skip over, no, I can't do it because of that. Skip over to the M&Ms page. Let's go to the top here. The thing in red that you just saw, please don't do that, okay? It says don't do it. All right. I might, I don't know if I can pause the recording or not. I might just keep it going and count the M&Ms and tell you all to skip forward through that. Okay, so the question is, I don't know if y'all can see this or not. Maybe not, but that's okay. I have a brand new pack of M&Ms that I just opened. M&Ms just opened. Okay, and I really like M&Ms, and but I hate it when people mess with my M&Ms. And sometimes maybe there's some guy that I can't trust at the M&Ms factory, and maybe he's taken away some of the blues that are the best, or maybe adding in a bunch of the, I don't know, the oranges, which nobody likes the oranges, right? And so every time I eat a bag of M&Ms, have to prove to myself with math that nobody has been messing with my M&Ms. And chi-squared is a great way of doing that, because a while back, M&M Mars released their formulas. They said, this is our formula for making a bag of M&Ms, how much you should expect to get. So they said, let's see, they said, and by the way, I have plain M&Ms right here. So I should expect 13% brown, 14% yellow, 13% red, 16% green, 24% blue, and 20% orange M&Ms. And this is what I've got, right? So you guys can see brand new M&Ms right there. So okay, so we have our expected values right there, kind of. We have percentages. Percentages are not necessarily expected values. I'll explain that here in a second. But first, I want to make sure nobody was messing with my M&Ms, because then I can eat my M&Ms. So, okay, so I need to count these really quick. But basically, we also need to start off, and if we go in order, I'm not going to read all this kind of stuff. The null hypothesis, you guys know that, right? It's that there is no statistical difference between my observed M&Ms that I have in front of me and my expected M&Ms that M&M Mars said I should get. And that means my hypothesis is the opposite of that, that any differences are due to some weirdo at the M&M Mars factory messing with my M&Ms. So we want to reject the hypothesis and accept the null. And I can't actually eat the M&Ms until I've done that, because that'd be gross. Who knows what they're doing to the M&Ms, right? Okay, so there's the chi-squared value. We just went over that. What we need to do is this, and then I'm gonna have you guys finish it on your own. Okay, brown. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 brown M&Ms. Blue, 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 18 blue. Orange, 2, 4, 6, 8, 9. I have 9. Green is 2, 4, 6, 8, 10, 11. Red, 2, 4, 6, 7. Yellow is 2, 4, 6. 6. Okay, so those are the observed values that I just got right here. And so that would be a total of, clear, equals 9 plus 18 plus 9 plus 11 plus 7 plus 6. I have 60 total M&Ms right there. So my observed values are right there. Expected values, that's where you're going to start. Okay, so you guys start on expected, the observed minus expected, the observed minus the expected squared, and then you're going to go all the way through until you get your chi-squared value right here. You've got a couple of questions about degrees of freedom right there. Read, it does explain things. There's that exact same p table. We're looking for our chi-squared value, degrees of freedom, p value, percent of time you would expect these results due to random chance. Those are the same thing. Accept or reject your null hypothesis, accept or reject your hypothesis. Was somebody messing with my bag of M&Ms? How would these results be altered if we took data from the whole class? I usually have the class combine all their data into a larger sample size, because that helps us learn about the importance of sample size and why scientists test medications on thousands of people instead of just 2. But skip the red thing. That's the group data. We just can't really do that. And then there is a practice question that gets back to biology with a dihybrid cross Punnett square. We haven't covered these yet, and you might not remember how to do them, so I gave you the observed. You just need to get the expected, that I believe is given to, oh no, the expected is not given to, I gave you the observed. Ooh, okay, that's right. I want to see who remembers how to do the dihybrid cross Punnett square. Although it did give you the outside of the Punnett square there, so that kind of simplifies it. And so what we can do is in the synchronous time on the 23rd, we can come in and work on this together if we don't remember how to do this kind of stuff. So, all right, I'm going to finish this math, and if nobody has been messing with my M&Ms, I'm going to eat my M&Ms, and then I will hopefully see you guys, and I'll let you know about you guys can let me know about the results that you got and see if they match up with mine when we meet in synchronous time. Let's see, what else do we have? Oh, there's a test on, let's raise this a little bit. There is a test on Friday, and the test is going to be really similar to the quiz, just a little bit longer, probably a longer free response question, because I want y'all to see one of the longer, like 10-point free response questions. And so we will do that and take the multiple choice questions. Just be ready, study Unit 1, go back and look at the Unit 1 outline. It covers, natural selection, animal organization, homeostasis, basic chemistry, and just like the definitions of biology. So let's see if I can stop sharing. Okay. I hope y'all are having a good day. If we were in class, you would now be eating your M&Ms. But as it is, I'm going to prove that nobody messed with them, and then I'm going to eat my M&Ms. So I will see y'all this afternoon. Bye.